In this video, we are going to be talking about radioisotopes, which still has to do with nuclear chemistry. So the first thing we're going to talk about is radioactivity, which is the process of the spontaneous decay and transformation of unstable atomic nuclei accompanied with the emission of nuclear particles and/or electromagnetic radiation. So the unstable nuclei is called the parent nuclide, and then the nuclei that results from the decay is known as the daughter nuclide. So if we see at the bottom of this slide, we see that our parent nucleus, uranium-238, is forming its daughter nucleus, thorium-234, by giving off an alpha particle, which it's going through alpha decay. There are three major forms of radioactivity that we're going to discuss, but the first type is called an alpha particle, which is symbolized by the Greek letter alpha. An alpha particle is composed of 2 protons and 2 neutrons and is the same as a helium nucleus. It has a charge of +2, and when a radioactive atom emits an alpha particle, the original atom's atomic number will decrease by 2 because of the loss of 2 protons, and its mass number will decrease by 4 because of the loss of 4 nuclear particles. So if we look at our example at the bottom, we see that we have uranium-235 over 92, and that is going to give out an alpha decay, which we have our alpha particle, that helium-4 over 2, which can also be written as alpha 4 over 2, either way is correct, and forming that daughter nucleus of thorium-231 over 90. The second type of radioactive emission is called a beta particle, which is symbolized by the Greek letter beta. A beta particle is an electron ejected from the nucleus and has a -1 charge. The net effect of beta particle emission on a nucleus is that a neutron is converted to a proton. The overall mass number stays the same, but because the number of protons increases by 1, the atomic number goes up by 1. If we look at the example at the bottom of this slide, we see that we have our parent nuclide, carbon 14 over 6, producing our daughter nuclide, nitrogen 14 over 7, plus that beta particle. But also remember that beta particle can also be written with our beta symbol and then 0 over -1. Our third major type of radioactive emission is not a particle, but rather a very energetic form of electromagnetic radiation called gamma rays, symbolized by the Greek letter gamma. Electromagnetic radiation can be characterized into different categories based on the wavelength and photon energies. If we look at the example at the bottom of this slide, we see that technetium is going through gamma radiation by having its same nuclide but giving off gamma rays. So because gamma rays have the shortest wavelength, normally they will not also give off a beta and alpha particle, but as the wavelength gets longer, then it will determine what kind of particle is let off with it, and that will either be an alpha or beta particle, or it could be both. On this next slide, it shows distinctions between alpha particles, beta particles, and gamma rays. So if you want to pause this video and look at their symbols, identity, charge, mass number, and penetrating power, you can go ahead and do so. Now that we have finished discussing the major forms of radioactivity, we are going to talk about the difference between fission versus fusion. So fission is the release of energy by splitting heavy nuclei. So if we look at our picture below, we see that our heavy nuclei is being split into 2 light nuclei through energy, where fusion is the release of energy by combining 2 light nuclei. So if we look at our picture below that, we see 2 light nuclei coming together using energy to form a heavy nuclei. Now that we have discussed the major parts of radioactivity, we're now going to transition and talk about radioisotopes. But before we do that, we are going to define what an isotope is. So isotopes are the atoms in an element that have the same atomic number but a different atomic mass. They can be stable or unstable and can be formed naturally or artificially. So if they're formed naturally, they are found in nature, and if they are formed artificially, then they are manufactured in a nuclear laboratory. Now that we have defined what an isotope is and learned that it can be unstable or stable, we are now going to discuss radioisotopes, which are radioactive isotopes of an element. They can also be defined as atoms that contain an unstable combination of neutrons and protons or excess energy in their nucleus. So with this being said, radioisotopes are always going to be unstable. Atoms with an unstable nucleus regain stability by shedding excess particles and energy in the form of radiation. The process of shedding the radiation is called radioactive decay. And we have learned that radioactive decay could be through beta particles, alpha particles, or gamma rays. The radioactive decay process for each radioisotope is unique and is measured with a time period called a half-life. So one half-life is the time it takes for half of the unstable atom to undergo radioactive decay. There are many applications of radioisotopes. So on this slide, I have a list of applications of radioisotopes. So I have medicine, industry and technology, agriculture, art, archaeology, research, and pharmacology. The last thing we're going to discuss in this video is radioactive dating. Radioactive dating is also known as radiometric dating and determines the age of materials such as mineral specimen by using radioactive isotopes and half-lives. It is the principal source of information about the absolute age of rocks and other geological features, including the age of the Earth itself, and it can be used to date a wide range of natural and man-made materials. If we take a look at the picture on this slide, we see how a fossil's age is determined by measuring the amount of C14 radiocarbon that it contains.